Hello and welcome once again for another ES340 video. This will be day 8 part B. So now we've gotten into the control volumes, of course, and we're going to discuss now conservation of energy in a control volume. So last time we really were discussing conservation of mass, and now we'll get into conservation of energy. Now, for closed systems, I just want to make this map back in your head between the two. We'll put a little box here. For closed systems, delta E is equal to delta PE plus delta KE plus delta U, and delta E is equal to Q minus W. Okay, but now let's actually write out some of these terms. So delta E then is equal to 1/2 m V2 squared minus V1 squared plus mgh2 minus h1 plus delta, U, capital U, capital U2 minus U1. Right, that was our, if I were to write it out in terms of the various things, that would be the expanded version, right? Now for control volumes, mass is changing over time. This is really a key part of this problem. And since the mass is changing, that means that notice that we have a term that contains mass here, we have a term that contains mass here, right? So this means that I wrote this in terms of capital M, but we're going to see in a moment that we also are going to have U2, for instance, would be equal to M lowercase u2, correct? The specific volume. So inside of here, the fact that mass is changing also is going to affect even the internal energy of the system. Okay, so because of that, then I just wanted to map this back to here so that it doesn't seem like it's just popping out of nowhere. DE, now this was delta E. Now we're asking, how is the energy changing in time? Right, this was just the total change in energy in a closed system. Now we actually are going to have a rate of change over time for the mass, for the control volume, because the mass is changing. Now this is going to be equal to m I dot. So this is all of the inlets, right? All of the mass that was flowing in the inlets times lowercase ui. This is obviously my specific internal energy, plus vi squared over 2. And this would be a single, I'll write that in a moment. This is for single inlet and single exit. Again, we could write it with multiple inlets, multiple exits. I'm going to do that in a moment. Plus GZI. Oh, sorry, these should have been Z's. I forgot your textbook likes to use Z for height, because H is the specific enthalpy, lowercase h. So I have to be careful with my notation here. minus ME dot UE plus VE squared over 2 plus GZE. Okay, so this is mass that's flowing at the inlet, so we're getting an input it's going to change the internal energy because we have mass flowing in. It's going to change the velocity again because we have mass flowing in. We have now we have a flow of, say, a thing of air or something like that, and we have potentially a change in height, as we'll see in some problems, and similarly we have something that's happening at the exit. So this is a single inlet, single exit version of the energy change rate, the energy rate in a control volume. Okay, and obviously that would be equal to Q, in this case dot now, minus W dot. Or this is going to be, sorry, plus Q dot minus W dot. This is going to be the way we write the change in energy, the total change in energy. And again, it's going to be related to our problems that we had here. But now, this is the total change in energy in the system. So I have some heat flow rate, I have some work flow rate, and that's going to give me my total change in energy across the control volume. Now, if I wanted to say this was a single inlet, single outlet problem, but imagine 3 inlets and 0 outlets, 0 exits, then my equation would look something like this. 3 inlets, inlet M1 dot, M2 dot, and M3 dot. Then this would obviously be the same, it would be the same exact idea. But now I'm going to have to say M1 dot times U1 plus V1 squared over 2 plus GZ1 plus M2 dot U2 plus V2 squared over 2 plus GZ1. And there's a reason why I'm writing this, because I noticed that if I put it in the sum, sometimes that doesn't map back into people's brains. So I just wanted to write out a couple of examples like this. Times U3 plus V3 squared over 2 plus GZ3. Okay, and that would be plus Q dot minus W dot. Okay, so that would be, I should have put this like this so that it's inside of there. There we go. There we go. So this is the 3 inlets and 0 exit case, and in general, as you can imagine, dECV dt is going to be equal to the sum over I mi times ui plus vi squared over 2 plus gzi minus the sum over e, all of the exits, this is a dot by the way, times ue plus ve squared over 2 plus GZE plus Q dot minus W dot. Okay, so that's the general case for energy flow, and it's very similar to what we have up here, but now we're having rates of change, right? Because of what's going on, we're going to have these different rates of change, and that's what's going to give us our energy balance. Now, thinking back to steady state as an example, you should already imagine that dECV dt is going to be equal to 0, because remember, in steady state, all properties are constant in time, and that includes energy inside the control volume. So that's going to be something, and we're going to talk about steady state in a moment, but I just want you to keep mapping these things back together in your mind. Now for W dot, your book likes to think about changing this to splitting up work. So you can split up the work into two pieces. The W dot is equal to WCV dot, where this is work done by, well, it's power really. This is the rate of change in time of work, which gives you power. But we'll just keep thinking of this in terms of work because it's easier to discuss it that way. Work rate, I should say, done by things like electric motors and other mechanical inputs. But there's also going to be work related to the fact that we just have this flow. So this is one part of that, plus a term like this. This would be like a single inlet and a single exit type problem. Okay, so it would be something like this, which means or plus ME dot, again, single inlet, single exit case. Rather than writing the sum out, we can write it in terms of single inlet, single exit, PE VE, where that's the specific volume now, minus MI dot PI VI at the inlets, right? Because these are the like little work terms. It's easier to see it this way. And these capital V's, by the way, are volume. That's the annoying thing about your textbook. It likes to switch back and forth. And supposedly the V is supposed to look different. Oh no, that's the velocity, sorry. Velocity. See, even I get confused by their changing in notation. But down here, this is the specific volume. Okay? So these little work terms obviously are related to the fact that we have this flowing mass coming into and out of the system. So we break it into two pieces, and this is called the flow work, by the way. That's the name of that. Okay. So we've discussed the work now, and we'll do example problems, so don't worry. I know that there's a lot kind of getting flung at you at the moment, but I think it'll all make sense soon enough. Now, in the one-dimensional case, 1D flow case, then we can write in terms of, again, single inlet, single outlet. We can write DECV dt is equal to Q dot CV minus W dot CV. So notice we're going to be ignoring in this case the total flow work, including the work done by the mass flow, and we'll only care about those other inputs, right, in this equation. Plus MI, stuff that comes from electric motors and other things like that. Plus MI dot UI plus PI VI. See, now we're accounting for these pieces inside of here, right? We've moved this inside of here. So now this is the work done by those motors and things like that. And we've moved this term inside of here because it's convenient. Plus GZI minus ME. I'm sorry, I run out of space because this obviously is a lot to write. I think probably this is fairly simple to work out all of these terms, but this is going to be this is the hard part. Typically, of this is actually going to be making sure that you have the correct units for everything, specifically things like this, right? So you'll have to be careful, and this. So you have to be careful that you're accounting for the proper units. But in any case, we can also write this in terms of the specific enthalpy. And usually this is convenient. So, in other words, it's going to be a pain in the neck, typically, if we use the internal energy. And because, note the following, H is equal to U plus PV, right? Well, notice inside here we have U plus PV. So it's going to be typically when you're going to your tables, when we're dealing with the 1D flow of a control volume and we're dealing with that energy balance, it's really going to often just be easier to do it in terms of the enthalpy rather than the specific internal energy. So DECV dt is going to be equal to Q dot CV minus W dot CV plus MI dot HI plus VI squared over 2 plus GZI minus ME dot HE plus VE squared over 2 plus GZE. So notice that, like if I just have to look up the specific enthalpy on the table, that's going to be a lot easier than having to, calculate out, especially if I have multiple, this is single inlet and single outlet. But if I have to go back and look up, if I had multiple inlets or multiple outlets, and I have to go back and look up U each time, figure out the pressure times the specific volume each time, that might get a little bit tedious. So it's much easier to use this formulation when we're dealing with this. And this is, again, 1D flow. But typically we'll be using the 1D flow. Okay, let's write out the general case just so that we have it. dE dt is equal to Q CV dot minus W CV dot. And note that these terms could also actually be sums of other terms, right? Because you might have multiple things doing work or something like that. But we don't commonly run into those kinds of problems. Just occasionally. I forgot my MI. Minus the sum over E of ME dot HE plus VE squared over 2 plus GZE. Okay, so I could have multiple exits or multiple entrances and inlets and have to sum up a whole bunch of those terms, right? That can potentially happen. So just keep that in mind when we're dealing with these problems. Now, steady state. Control volume. Energy rate balance. Okay, so in steady state, recall, and we're going to see this over and over again, properties are constant in time. Including the energy, because energy is, of course, a property. So dECV dt at steady state is 0. Or to write it more explicitly, it's equal to 0, right? So what does that mean? Well, then that means that this implies that Q dot CV minus W dot CV has to be equal to M, let's do the sum so that it's a general form, MIHI plus VI squared over 2 plus GZI this is going to be E, sorry, minus, notice that it flips the sign here, that's why I got messed up there, I'm really messing myself up, it's I here, these should have been E's. Okay, and that's because I moved everything over, but that's because this is equal to 0, right? Because that's equal to 0, I can move all those terms over to the other side and get something that looks like this. So this is something that we will be dealing with quite frequently for the rest of the book. Actually, what's going to end up happening is we're going to be dealing with these cases. A lot of times we're going to have steady states. Steady state's going to immediately tell us this. Although we can have cases where it's transient. So we're going to have to identify in the problem, are we talking about steady state or are we talking about transient? At steady state, this is equal to 0, simplifies things a little bit. In the general case where it's not in steady state, it could be transient, then we have to deal with the full equation, right? So we're going to have to separate out all of these scenarios. And what we're going to do in the next set of lectures, which will be short, is discuss a variety of different cases, nozzles and diffusers, and a variety of other kinds of special cases, turbines, and so on, compressors, things like this, different variety of cases, and how we can deal with the energy rate balance equation, and in those variety of circumstances. But we're always going to want to identify in the problem, are we at steady state? Are we not at steady state? Can it be assumed to be an ideal gas, or am I going to have to go to the tables in order to find these values and things like this? Okay, so keep all of that in mind as we go on. But that's all I have for this video. Hope to see you again soon.